Notice that if you are finding the difference between your x value and the mean is 4.6, right? So notice we should get the same thing for these two 5s, because 5 minus 4.6 is 0.4 no matter how many 5s we have, right? 4 minus 4.6 would be negative 0.6. Okay, notice these two 4s are the same as each other, right? 0 minus 4.6 would be negative 4.6. So all of these numbers that I'm writing here are the difference between the x value that you're currently on and whatever the mean was. So notice these values in this second column are not going to be correct unless your mean is correct, right? But then it's just a matter of subtracting value minus mean, okay? So what are you supposed to do in this last column? You take what you got in the second column and you do what with it, basically? Square it, okay? So before I list for you all of those values, notice that anytime you square a number, whether it's positive or negative, what happens to it? Like, what's a negative number times a negative number? It's positive, right? So everything in this column should be positive. So all of these numbers squared give us the following. Notice that the larger the difference was in the second column, obviously the larger the squared version will be in the third column. So that's what you should have gotten there. If you add them all up, you get 50.4. So the point of the table is purely organizational, because what we need for our formula for standard deviation is we need the sum of all the differences between the x's and the mean squared, okay? So that's what this gave us, right? This gave us this, and then that is what's going to go in our formula. So I kind of set that up for you last time. And then if you take the square root of 50.4 divided by 9, you're going to get about 2.37. So the standard deviation is representative of how far in general the numbers are from the mean, okay? In other words, how much do the numbers deviate from the mean, which is what we expected them to be, okay? So by the way, notice things that are close to the mean have a less deviation, right? Because they're not as deviant from the mean. Okay, so deviation describes how far apart the values are from what we expected them to be. And what we expect them to be on average is what? 4.6, but some of them are smaller and some of them are what? Are bigger. And this is just an overall description of how far the whole list is away from the mean. Okay, just so you know, lots of areas of business use standard deviation. Okay, lots and lots. Okay, the insurance industry uses it heavily to talk about predictability of things like car accidents, or the life insurance companies use it for predictability as far as deaths go, right? Because they want to know, as morbid as it is, if you're a life insurance company, you've got to know what the chances are that a 40-year-old smoker will die this year, okay? Because that's how you're going to decide how much to charge him for life insurance, okay? So they don't want to pay out claims to a bunch of people, right? So they need to know those things. Some other ways that standard deviation is heavily used is in the stock market, okay? So the stock market goes up and down every day, right? Even multiple times a day. And so how volatile it is, in other words, how fluctuating the quantities or the dollar amounts are, all has to do with standard deviation, right? So if you have a low standard deviation for a certain stock, what that means is it's fairly predictable, okay? It's staying pretty close to the mean like we expect. If you have a really large standard deviation, it means that it's wildly going up and down and you can't really depend on what it is, okay? And so if you ever decide to invest in mutual funds or stocks, all stock companies have to give you a couple of pieces of information, and one of those pieces of information is a descriptor of how volatile the stock is. How much is it wildly changing from this dollar amount to this dollar amount, because you need to know that, right? If it's your money, you need to know how predictable it is. So how predictable is it that you can plan on it being close to the mean, or are you going to expect wild changes, you know, low and high, and that's what you don't want with your money? I think we can agree with that, right? Okay, so we're going to use standard deviation for some other things a little bit later today. But going off of this problem that I had you finish from last class, I want you to tell me how many values in the above list are within 1 standard deviation from the mean. In other words, either high or low, how many of these values fluctuated kind of closely to the mean? Okay, so just to remind you, our mean was X bar was 4.6, and our standard deviation we got was about 2.37. So what we're trying to find is how many values in the list above were only bigger or smaller from the mean by 2.37. Okay, so in other words, you just need to count these values that are 2.37 or less, either positive or negative though. Okay, so we have 10 values, right? So how many of them are within 2.37 away? So just to recap, this one is, right, because it's only 0.6 away. This one is, it's only 0.4 away. This one is not. Why not? Because it's 4.6 away from the mean, right? So it's too far. So if we count them, we have 1, 2, 3, 4, 5 here, 6, and then these don't count, right? They're just a little bit too much. Does that make sense? Like if you added 2.37 to 4.6, you get a little under 7. So it looks like there are 6 out of 10 are within 1 standard deviation. So basically that represents 60% of the values lie within 1 standard deviation. Okay? In other words, they're predictable to the point where we can guess that they'll only be a little bit higher than the mean or a little bit lower. So in case that was problematic for you to figure out, let's go ahead and write down how you can figure it out if you don't want to look at your table. So we were looking for things that were no more than 2.37 away from 4.6. So the low value we were looking for was 2.23. And then we were looking for nothing bigger than whatever we get when we do 4.6 plus that standard deviation, which is 6.97. Remember how I said those 2 entries of 7 were just barely too high? And note they are, right? So 7's just a little bit too big. We weren't expecting anything higher than 6.97. So let's take that same logic, and I want you to tell me how many values in the list are within 2 standard deviations. From the mean. So let's do a calculation here. So what I mean by that is we don't want to go any smaller than this. So it'll be 4.6 minus 2 times the standard deviation. That's what 2 standard deviations mean, literally 2 of those sections of 2.37. So notice we get a negative value here. It's actually negative 0.14. So this is the low end. By the way, we don't even have anything negative, right? So all of the values are going to be kind of within that threshold so far. So let's go larger. Larger than the mean would be 4.6 plus 2 times the 2.37 standard deviation quantity, which is 9.34. So anything between these two values are considered within 2 standard deviations, okay? So let's look back at our list, and I'll move it if you're still writing that. But how many of these values fall within the low and the high that we just mentioned?
We're looking at the original value.
Yep, original values. So how many values fall within negative whatever, which we don't even have any negatives, right? And 9 point something. All 10 of them, right? So it's 10 out of 10 or 100%. So 100% are within 2 standard deviations. Okay, so we're going to go back to this within 1, 2, or possibly 3 standard deviations in just a minute. But I want to show you kind of an alternative way to find standard deviation. It's really not different. It's just you don't have to have a table if you think making the table is kind of tedious. So I'll agree that I think the table is a bit tedious, but it does help you organize your data, right? And it does make it nice because you're only doing one operation at a time. So just to recap before I give you another one, the table first just has you subtract, right? And then it squares those values, and then you add up the sum and put it in the formula, right? So it just kind of breaks standard deviation into baby steps, right? It breaks this sum quantity into baby steps so that you're not having to do it all at once. However, I think some of you might prefer to not maybe do the table because, like I mentioned, it is a little tedious. So let's say that I asked you to find the standard deviation of the following 6 values. All right, so before we start, let's talk about what our formula for standard deviation is. Recall that S is going to be the square root of, what does this symbol mean that I just wrote? Sum, so it's the sum of the differences between the X values and the average squared, and then over N minus 1. So the hard part of this formula is coming up with that sum amount, right? That's why we had the table before. It helped us organize all of that stuff. Okay, so the first thing we need to do, though, is find the average. So to find the average, what do we do, basically? We add up the numbers and divide by what? However many there were, right, which in this case is 6. So do take caution with this mean because it needs to be right moving forward. Okay, but what you should get here is that X bar is right around 4.26 with a bar over it. So in other words, it's 2.66666 forever, right? So you need to kind of carry that out pretty far when you're trying to do a calculation. So rather than do the table, you can do this, and then you can just decide which version you like. You can just show this and have a big old fraction over N minus 1. Okay, so rather than showing it in table format, you can just be like, okay, first I'm going to take the first value minus the average squared, and then I'm going to take the second value minus the average squared. And then I'm going to take the third value. I think you see the point, right? And I'm going to do that until I go all the way through the list. So I'm going to be kind of lazy here and say all the way to the end, which the last one would be what? 3.6 minus that average squared. So regardless, like the sum part is the tedious portion of it, right? So notice I would do this and make sure you fill in the ... right? So I didn't write down, because frankly I ran out of room. I didn't write down the 6.2 or the 5.2, but it would need to be included as well. So you might find that you like this method better, and then it's just kind of up to you which one you decide to use. So here I get that S is about 1.166. So I'm going to kind of circle that answer. So if you prefer, you can do the top portion of that fraction in a table format, but however you do it, you need to verify that you're getting the correct answer there. Okay? And as far as the 4.26 with the bar over it, you would just probably need to list quite a few sixes, right? So we don't want to round in the middle of the problem. So you would just need to do like 4.26666, like do a few of them. Okay, so because you're not going to be able to enter a bar in on your calculator. Does that make sense?
It's
Like you're
probably
going to.
not possible to carry the answer over, if that makes sense.
It actually is. So you can do that, and how you do that, just so you know. So I was going to talk about that too. But we can talk about it now. So I'll just start you off. So let me get the average kind of in there. So you would do 3.3 plus parentheses. So 3.3 plus 3.5 plus 3.8 plus 6.2 plus 5.2 plus 3.6, all divided by 6. And let's say that you didn't want to have to type in all those decimals. You wanted to hold the answer. You can just use the answer key. You just have to be careful. So it's going to be the square root of 3.3 minus the answer. So notice how it literally says ANS for answer, and what that does is pulls the previous answer without you having to retype it. And then you could say plus, and I need another parentheses here. So the reason I need another parentheses here is I need a parentheses for the whole numerator. I'm looking ahead. So the next one would be 3.5 minus the answer, parentheses squared, plus all the way through, and then divide by 6 minus 1, or divide by 5. So you can do it that way as well, and you'll get a more accurate answer if you do it that way, for sure. Okay, so just so you know, if you haven't ever used that button before, it's second and then the negative key. If you look above the negative sign key, it says ANS, and that just pulls the previous answer in all of its decimal places. So it's actually really convenient to use in a case like this where you don't want to have to enter in a whole bunch of decimal places over and over. Okay, just remember that in any problem we want to try to round how many times? Once, right? So if we can help it, we want to round one time. So that is why it would be kind of especially important on this problem. Okay. So, by the way, this has a smaller standard deviation than we got in the previous example. So what does that mean? Standard deviation measures what? Distance from the mean, right? It measures how far all the values are kind of varying from the mean that we expected, right? So basically, what does it mean about this list? It means this list is like tighter, right? This list is more condensed. This list is closer to the mean of 4.26 than this list was, okay? And if you kind of look at the numbers, you'll see that's true, right? The mean here was 4.6, and we had some pretty big fluctuations, right? We went all the way from 0 to 8, so pretty wild on both sides, right? Whereas this list, do you notice that everything stayed pretty darn close to 4.6. The furthest thing away is this 6.2, right? But everything else is pretty close. So that is why we got a smaller standard deviation. Okay, so all a smaller standard deviation indicates is that the values are not as volatile. They're fairly predictable because they're all kind of clustered together. Okay.